In this video, I will present some of the math behind the bivector spin. You can skip it, since it's not for everyone, but some want to know. The goal is to show how a bivector is described classically using the language of geometric algebra, which is natural. Then I discuss measurement and compare the standard model with the bivector standard model. A starting point and the underlying basis for much about spin lies in the geometric product of Pauli matrices. Note that the two terms are exclusive, since I cannot simultaneously be equal and not equal to J. It represents the two basic properties of nature, symmetric and antisymmetric. That complementarity was expressed by Niels Bohr in his Copenhagen Interpretation, and that one excludes the other. That is, position and momentum do not exist simultaneously, and that is the heart of the Einstein-Bohr debates and the famous EPR paper. However, here that is not the meaning of complementarity. The two terms refer to different spaces, and we can only measure in one. For example, one space is a laboratory fixed frame, and the second is the body fixed frame. That is, the internal bivector engine is in the body fixed frame, and the torque, or the force, is in the laboratory fixed frame. Both exist simultaneously and indeed are intimately related. The two spaces are dual and complementary, but not exclusive, as Bohr believed. After studying the classical bivector, the correspondence to quantum naturally follows, and I just wrote them down. The first term is the usual external vector motion around the torque axis. This spins the plane, which becomes locked mass. So from the laboratory fixed frame, intrinsic angular momentum is observed as a spinning vector. The bivector motion is not visible. This is the origin of the word intrinsic in quantum mechanics. Defining classical spin as a bivector translates to quantum mechanics as I times sigma, which is a bivector of Pauli matrices. Although Pauli matrices are considered quantum, describing spin up and down, in the bivector standard model they describe the chirality of left and right, which is not quantum. Indeed, all the classical properties smoothly transition between classical and quantum. Since parity, time reversal, and charge conjugation are conserved classically, so it must be in the quantum domain. The famous 1956 experiment of Wu is not wrong, only misinterpreted. Finally, one is naturally led to define spin as a vector and a bivector, which gives a rotor or a quaternion. The usual definition of spin in quantum mechanics neglects the bivector, since only the vector motion can be measured, that is sigma, in usual polarized experiments, and the second term is zero. However, EPR coincidence experiments measure the correlation between a product of spins, one at Alice and one at Bob, and in that case, both terms are relevant and lead to an explanation for the violation of Bell's inequalities. The triangle is correlation between two vectors, and the moustache is correlation between two bivectors. The simulation was done classically. We are then led to rejecting Bell's theorem and the notion of non-locality. Since spin in the bivector standard model gives a quaternion, I call it quaternion spin. Usually, quantum classical correspondence is given by energy, momentum, and angular momentum, and they become classical as Planck's constant goes to zero. There is no Planck's constant in the spin correspondence. Also, energy, momentum, and angular momentum are continuous variables, and spin correspondence is discrete. Planck's constant is defined as the angular momentum of a bivector when it attains the quantum domain. I will discuss Planck's constant later. The cones of angular momentum are found by solving Euler's equations. First, for constant precession, no torque, the system is conservative, and we get the substantive derivative. For the bivector, there are two independent equations, one for each axis, but they must be solved with equal and opposite energy, which is energy conservation, and with also equal phases. Therefore, the two frequencies, omega 1 and omega 3, are equal and opposite. The uppercase omega is the frequency about the torque axis, which is half that of the cone counterprecessions. This gives the two cones expressed within the interaction plane 1, 3. I use theta, the angle between the axis, and its angular momentum vector, which is equal for the two axes. But let's convert to phi, the angle between the two angular momentum vectors. We transform to the bivector basis. Now it is clear that at phi equals 0, the two angular momentum vectors lie along the bisector, and the cones come in and out of resonance along 1, 3. At resonance, which is phi equals 0, the tandem precession leads to constructive and destructive interference purely through their precessional motion, leaving the constructive resonant state along the bisector. Now we express this using geometric algebra. We start with classical spin, with angular momentum I just found, and calculate the scalar product and the wedge product, which we use to get the geometric product. This gives the complete dynamics from the body fixed frame. If the spin is unnormalized, then the geometric product is a unit quaternion and a phase. It changes the left-handed frame to the right-handed frame on permutation of 1 and 3, and it describes the energy mass through the two terms. As phi equals 0, a purely resonant spin is formed along the bisector as seen from the 45-degree angle and the length of root 2. I will not repeat this, which I discussed in part 4. This state, as emphasized, converts into mass, and all kinetic motion stops. The double helix wraps up reflection into a state of positive parity. As the two opposite helicities intertwine into scalar mass, which is all mass at phi equals 0, it is impossible that more torque can allow the two cones to pass. They are locked into their quantum state at phi equals 0. Adding more energy cannot be absorbed by the bivector. In the bivector standard model, there is no wave function collapse and no superposition. States rotate to different orientations. Measurement projects them, and then we renormalize the result. For example, suppose the axis 3 aligns and the axis 1 is randomized in a field, leaving only the 3 axes in the body fixed frame. Now rotate this to the laboratory fixed frame using the rotation operator, which is a quaternion, to get cosine theta. But cosine theta goes from -1 to +1, so normalize it to the limits of 0 and 1, giving the usual results from quantum mechanics, without superposition or wave function collapse. The results are probabilities in quantum mechanics, but definite physical orientations in the bivector standard model. One result is random, and the other is real. Spin up and down refers to the physical axes of a bivector being aligned in a field, not the abstract spin of a chiral vector in a Hilbert space. Keep in mind that this is not yet quantum mechanics, so the bivector here is still classical. Let's look at the key equations defining the dynamics of the bivector-based standard model. We start with the state operator ρ. Here ρ represents the geometric state of the system, built from the bivector structure of the boson. It is not a density matrix, as in quantum mechanics. It is a classical operator that expresses the orientation and internal structure. When the state rotates under the rotor r, we get a new state, ρ'. To compute the averages of physical quantities, we use the scalar part of the expression as shown here. This means rotate the state, apply the observable A, and extract the scalar part of the multivector. In the bistandard model, the expectation value A measures the geometric orientation and overlap between the rotated state and the operator. It is an orientation, not a quantum probability. Now, for dynamics, we define the classical Hamiltonian, where the classical Lagrangian describes the rotational energy and structure of the bivector boson. I discussed the Lagrangian elsewhere, but after bifurcation into the quantum domain of mass and energy, quantum Lagrangians for each are constructed, leading to quantum Hamiltonians. The evolution of the state operator is governed by the quantum Liouville equation or the von Neumann equation. This equation in the bystander model describes how the classical bivector state operator evolves due to the Hamiltonian dynamics. The commutator reflects rotational or internal changes in the structure over time. The key point is, in the bystander model, ρ is a classical state operator representing the real physical structure of the boson, not an abstract quantum object or a statistical mixture. First, the bystander model builds a classical structure which hosts the energy which becomes quantized. The Born-Oppenheimer approximation is an example, but the frame too can become quantized. Various functional groups can interact with others. Structure determines function. There is no structure in the standard model. For me, at the Big Bang, after electrons are formed, then the conditions are correct. They self-assemble into structures we have today. I will end with a calculation using the standard model and compare it with the bystander model. First, spin is postulated as a purely quantum property, and the two states of up and down are expressed as chiral vectors in an abstract two-dimensional Hilbert space with complex coefficients. Vectors in a Hilbert space can superpose. Bivectors cannot, meaning that if two states are valid, then so is any superposition. For example, expand any operator in its basis. Form the expectation value, which is weighted by the coefficients. Therefore, when measured, the wave function must collapse into the observed state with probability of P of AI. Collapse is a mathematical consequence of the linear 2D Hilbert space that gives the quantum definition of spin. Wave function collapse is the problem with quantum mechanics and its many varied and strange interpretations. There are no mechanisms and no determinism for wave function collapse. It just happens. There is no superposition in the bystander model because the structures are real objects in three-dimensional space. So we do calculations differently and project out the scalar or the invariant part of the multivector, and this gives the real structure. The standard model gives fuzzy states or superpositions which suddenly collapse when measured. No one can make sense of it. I will talk more about the standard model later, but here it is enough to say that fermions are replaced by the blades of bosons. Chiral particles like fermions lack the balance of two hands and have no physical basis to exist. If you lose a hand, you're seriously handicapped. Chiral fields that cover spacetimes with particles being excitations are replaced by the confined energy in classical structures. There is no superposition, no entanglement, no Born rule, no non-locality, no teleportation, nor even the superposition needed for Shor's algorithm, which is the primary motivation for quantum computing. However, the blades of bosons act like fermions, and the vector algebra of angular momentum still works. That is, the Clebsch-Gordon algebra remains unchanged, and the Wigner-Eckhart theorem and the Born rule also work, but only for SO3, not for SU2. Fundamentally, the standard model uses the Lie algebra of chiral vectors, and the bystander model uses the Clifford algebra of geometric algebra. Dirac chose the former, not knowing about the latter. Now you know there is a standard model of fermions and a bystander model based upon bosons. Which do you choose?